जो हमने क्लास में शुरू किए थे मैंने कहा
जो
anyway, I would like to define this square of the angular momentum operator. This is an angular momentum operator that has three components, Lx, Ly and Lz. Just like J, L is an angular momentum operator. The only difference is that this is specific to rotation in 3 dimensions. In the 3-dimensional Euclidean space. That's why L is called the orbital angular momentum operator. Now, these components satisfy the usual relationships for any angular momentum operator. That is, Lx commutated with Ly is iota h bar Lz, and all of its cyclic permutations. Okay, and we also know that like any other angular momentum operator, L square will commute with any one of its components. So it will commute with Lg, it will commute with Lx, it will commute with Ly, and so on. Okay, so it's just like an ordinary angular momentum operator. Alright. Now what I would like to find out, this operator in terms of theta and phi. Okay, so this is simply given by Lx squared plus Ly squared plus Lz squared. Okay, let's for example find out let's find out first of all Lx hat squared. Lx hat squared is Lx acting twice on some function. So Lx acting twice is minus h bar square. Okay. Now I would like to have this function act on itself. Okay. Which means I would like to have sine phi partial theta plus cotangent theta cosine of phi partial phi act on itself. Sine theta sine phi partial theta plus cotangent theta cosine of phi partial phi. Okay, ये ड्राइव किए थे आपने तो पहले Lx Ly Lz पोलर फॉर्म ये देखिए रिजल्ट्स आए. Alright, my Lx hat square is minus h bar square. Now sine phi, this operator acts on this operator, right? So I get sine square phi partial square partial theta square. Now this operator acts on this operator. I get from cotangent theta I get cosecant square theta sine phi cosine phi partial phi. Sorry. Yes. And cotangent theta sine of phi cosine of phi okay. Now when this operator acts on this operator I get sine square phi partial square partial theta square. When this operator acts on this operator I get sine phi cosine phi. The derivative of cotangent phi is cosecant square theta partial phi. Alright, that's it. Now this operator acting on this gives me cotangent theta cos of phi sine of phi cotangent of theta cosine of phi sine of phi becomes cosine of phi partial theta. Now this operator acting on this operator gives cotangent square theta cosecant square phi partial square partial phi square plus cotangent theta cos of phi cotangent square theta. This cos of phi, one derivative of this with respect to phi is minus sin phi partial phi. Okay. So this is my Lx hat square. Likewise, I can write down Ly hat square. Ly hat square is minus h bar square. Ly acting on itself. Now what is my Ly? Ly is written over there. So I have minus cosine of phi partial theta plus cotangent of theta sine of phi partial phi acting on itself minus cosine of phi partial theta plus cotangent of theta sine of phi partial phi minus h bar square minus cosine of phi. Now I take the derivative with respect to theta. This becomes cosine square phi partial square partial theta square. Now I take the derivative with respect to theta. The derivative of cotangent theta is cosecant square theta. Cosecant square theta with this cosine of phi minus cosine of phi sine of phi partial phi. Now I have this operator act on this. I have to take the derivative with respect to phi, so this becomes plus sine phi. So I get cotangent theta sine of phi sine square of phi partial theta. There is no other phi here. Now I take the derivative with respect to phi of this. I get cotangent square theta. This sine phi, the derivative is cosine phi partial phi plus cotangent theta sine of phi. This becomes sine square, cotangent square, partial phi square. My Lz square, likewise, Lz square is simply given by minus h bar square partial phi square. Now I can add these up. So if I would like to add them up, I can add this with this. This becomes this sine square phi plus cosine square phi is just 1. Sine phi cosine phi, this cancels out, this term cancels out with this term. This term cancels out to this one. So what I am left with overall is the following. My L square is equal to minus h bar square. Look at these terms. Partial square, partial theta square, partial square, partial theta square. Then I need to consider this term together with this term. This is plus cotangent theta partial theta. Okay, because this is cosine square phi, this is sine square phi. It just goes away. So I'm left finally with this term. This term once again is cotangent square theta. Cotangent square theta partial square partial phi square. partial square partial phi square, and I also get a partial square partial phi square over here. So if I do a little bit of simplification, this becomes minus h bar squared partial square partial theta square plus cotangent theta partial theta plus cosecant square theta, which is 1 over sine square theta partial square partial phi square. This is a very important result. Shows us something really interesting. Now, if we look at the Hamiltonian for the hydrogen atom, or for any central potential for that matter, any central potential system, we have minus h bar square over 2m del square plus some potential energy, central potential energy. Okay. We already cast this del square in terms of the spherical coordinates. We have minus h bar square over 2m. Now let's write this once again in the spherical coordinate system. You can look up your notes, and what we will have for this del square in spherical coordinates is the following. 1 over r square partial r square partial r plus 1 over r square sine theta partial theta sine theta partial theta plus 1 over r square sine square theta partial phi square plus of course a VR. Okay? So this is my Hamiltonian. I have just put this Laplacian operator in terms of the spherical coordinates. Now I can make one identification. If I look at this term, let's look at this term, or rather, let's look at this term. Let's look at this term. What I have in green. This term is really 1 over sine theta now I take the derivative. The derivative of sine theta is cosine theta partial theta plus sine theta partial theta square. So this is cotangent theta partial theta plus partial theta square. This is exactly identical to this term. And alright, and this term without the r square is identical to this term. Okay, so the Hamiltonian H I can always express as minus h bar square over 2m r square partial r square partial r, right, minus h bar square over 2m r square. Remember, this is VR is outside, this is here plus here. Okay, minus h bar square over 2m into this operator. So now what is this operator equal to? This operator is, if I put a plus sign here, I remove this h bar square. In place of this, I can write the square of the orbital angular momentum plus VR. An extremely important result. So we are talking about the central potential, just such as a hydrogen atom. In the hydrogen atom, we will specify the form of this potential energy. This potential energy for the hydrogen atom would be 1 over 4 pi epsilon naught minus sine E square over R square. So some potential energy that only depends upon the distance between the two bodies in the two-body quantum system. That is the electron and the proton. So look at this Hamiltonian. We have broken up this Hamiltonian or recast in a physically intuitive way. What we have here is a potential energy term, and we have an operator that corresponds to the kinetic energy. And the kinetic energy has now been broken up into two parts. It has been broken up into a rotational kinetic energy. This is angular momentum squared over, what is this object? 2mr squared. For any two-body system, what is this object? It's the moment of inertia. This is the moment of inertia for our two-body system. And if the objects, the two bodies in the two-body system, they have the same mass, we can use their mass. If they are of different masses, like an electron and a proton, we have to use a reduced mass, mu. Okay? Mu, remember, the reduced mass is given by m1, m2, m1 plus m, or u. So if you make this identification, this turns out to be the rotational kinetic energy. So this is the rotational kinetic energy operator. Okay? And it corresponds, it's proportional to the square of the orbital angular momentum operator. Hence, this term must correspond to the radial kinetic energy, because the kinetic energy will have two parts. If there is a rotational part that only depends upon theta and phi, there has to be a part that only depends upon the radius, because we have factorized the radial and the angular parts. Okay? So this operator tells us the radial kinetic energy is the operator corresponding to the radial kinetic energy. And we can also write this part as, like any other kinetic energy, as some PR hat square, the radial momentum square divided by 2m. Okay? Where I have defined this radial momentum square as it has been defined as, this is PR square over 2m. So this is 1 over r square minus h bar square 1 over r square into partial r square partial r. Okay. So this is my definition for the square of the radial momentum operator. Okay. So this factor turns out to be equal to an energy term, radial momentum square divided by 2m. So the expectation value of this operator will give us the radial kinetic energy, and the expectation value of this operator will give us the rotational kinetic energy. The expectation value of this operator will give us the potential energy.
म्यू का इस्तेमाल
म्यू, यहाँ पे अगर तो आप इलेक्ट्रॉन प्रोटॉन सिस्टम की बात करें हाइड्रोजन एटम की, जिसमें दोनों रोटेटिंग मासेस डिफरेंट हैं, तो you have each a reduced mass, okay, which is given by this formula.
So what's the operator for the other kind of
Right, PR square is the radial momentum square. So PR square over 2, all of this is the radial kinetic energy.
And all of that is the rotation.
All of this is the rotation. Okay. अच्छा, एक चीज मैं इस रेडियल मोमेंटम का जो ऑपरेटर है इसके बारे में बात करें, रेडियल मोमेंटम ऑपरेटर। ये देखिए, I need a momentum operator PR, radial momentum. I need to define something whose square gives me this. Okay. So suppose I define, remember this is also a definition, okay, this is a definition, because this term has to identify itself with the radial kinetic energy. There are only two parts to the kinetic energy, the radial part and the rotational part, that's it. So this is the rotational kinetic energy, this must correspond to the radial kinetic energy. Alright, so this is PR squared. Now I have to define PR by looking at this PR squared. So that is defined as minus iota h bar one partial by partial r plus 1 over r.
Iota is clear.
Sorry?
Iota is clear. Iota h.
तो नेगेटिव आ जाएगा
कोई बात नहीं, यानी कि आपने px जो हमने डिफाइन किया कार्टेशियन कोऑर्डिनेट्स में ही है ना, likewise for py easy. I would like to put in a minus sign, so I put in a minus sign. It doesn't matter if I square this becomes iota square, which is minus, and I have a minus here already, so it's fine. Okay. This minus sign is fine. I just want concordance with this formula. Now, can we prove that the square of this is given by this? Give it a try. First of all, what I would like to do, I would like to look at the definition of PR squared. Definition of PR squared is minus h bar square over r square, the derivative of this term with respect to r, which is 2r partial r plus r square partial r square, right? So this becomes minus h bar square 2 over r partial r plus partial r square, right? So I would like to prove that the square of this object equals this. Okay? Can you show me if it's really equal? How do I get? This one? So when this operator acts on this, first I take f as a constant, the derivative of 1 over r is minus 1 over r. Okay. So just I have to add these two terms. If you don't have a candidate function, you will be inclined not to include this term. Okay. So this is some small generally that I would like you to be aware of. So this is the radial momentum operator. This is the square of the radial momentum operator, and its expectation value corresponds to the radial kinetic energy. Okay. Now what we have here is our Hamiltonian H. Hamiltonian H is PR squared over 2m plus L square over 2I, I, where I is the moment of inertia plus the potential energy, right? I can put in a hat on this if I like. Now let's look at this operator. L square, does this come into the potential energy? Right. दूसरा आप ये सिर्फ रेडियल टर्म्स है, ये एंगुलर टर्म्स है, इसमें सिर्फ थीटा और फाई की टर्म्स है. The radial terms have nothing to do with the angular terms. So they mutually commute, right? Likewise, these terms mutually commute, right? Because this is a radial term, only has radial coordinates, this has theta and phi coordinates. So these commute. Okay? And we also know that all of this is p square over 2m plus pr.
So does it I depend on R?
Yeah, but r commutes with anything that has r in it. Okay? Because it's not a derivative, it's just r. Okay? So it commutes with anything that already is.
आपने L square को 0 लिए है।
Sorry?
या आपने L square को 0 लिए
L square को 0 नहीं है।
अच्छा आपने पूरे को जाए एक नोट करना है।
हमने देखा ये तो एक कांस्टेंट है ना। आपने देखा ये ऑपरेटर कम्यूट करता है इसके साथ ही नहीं। ये ऑपरेटर बाहमी तौर पे कम्यूट करते हैं। ठीक है? अब देखिए, this Hamiltonian also equals this form where p square is just p square of the momentum operator. Okay? Now r, this r, what is this r? This is just the distance of the electron or the system from the origin. This is simply x square plus y square plus z square under root. So this is the length of some vector. Okay? And this is p square is also the length of some vector. So lengths are norms. They don't have any direction. So they are just scalars. So this scalar and two scalars will mutually commute always. So this term also commutes with this term. The commutator is 0. Which means that the sum of these terms will commute with this term. So all three of these terms are mutually commuting with one another. Okay? So we've broken down the Hamiltonian into mutually commuting parts. This also means that if I look at the Hamiltonian, it will commute with L square. What does this mean? This means that the total orbital angular momentum of the system is a conserved quantity. Because this really means that we already know that d by dt expectation value of A is given by iota, is given by the expectation value of the commutator of A with the Hamiltonian with the factor I over h bar. Okay? So if an operator commutes with the Hamiltonian, then the expectation value of that operator is constant, is a station. So this is a station. The expectation value will not change with time. Okay? This is something we proved in the previous course. So this means that the total orbital angular momentum of the system will not change. And this is a direct consequence of the rotational symmetry of this problem.
H will be counting with all three terms.
H, yes. Another property is, we know that L square commutes with LZ. Okay. So this also means that the Hamiltonian will commute with LC as well. Why is this true? What does this physically mean? This physically means that, now what is LZ? LZ is a generator of rotations about the z-axis. What this means that if I take my central potential system like the hydrogen atom and rotate everything about the z-axis, nothing is going to change. The time evolution of the system is going to remain the same. Okay? If I rotate the Hamiltonian about the x-axis, will anything change? No. Because there is no preferred x, y or z axis. So I can take either of the three axes and the Hamiltonian will commute with the angular momentum operator about either of the three axes. So now we have a set of three operators. We have the Hamiltonian, we have L squared, and we have LZ. Now all three three of these operators are usually commuting. Okay? So they will have a common eigenbasis. Right? The eigenbases are labeled, of course, by three numbers because you have a three-dimensional system. The eigenstates of this operator are labeled by ML. We already know that. The eigenstates of this operator are labeled by N. The eigenstates of the Hamiltonian are labeled by the principal quantum number N. So we can define a set of eigenstates which is a common eigenbasis to all three of these commuting observables. Okay? Remember, here we are ignoring the spin of the electron. So far, we are ignoring the spin of the electron. Really, we have to do the spin of the electron, but since we're talking about three-dimensional wave mechanics and the Schrödinger equation, which does not give you the spin, Schrödinger equation doesn't give you the spin. Hence, we suffice ourselves in dealing with these three operators, which are mutually commuting. They form a complete. Hence, their eigenstates are. They have a common eigenbasis, and this will form a complete set for the Hilbert space. And in other words, if this Hamiltonian operator acts on this state, what will we get?
So we will get N into
N? No, we get the energy, which is labeled by N, which only depends upon N. N, L, and N. Right? We will not get N. If we have L square operator, and this acts on one of its eigenstates, what will we get? We get h bar square L into L plus 1, like any angular momentum operator. N, L, M, N. If we have LZ acting on the state, we have h bar Mn, N, L, M, N. And these M, L, L, and N are usually constrained. This is something we've already seen. Okay, and these quantum states, they can also be written in the position basis. So in the position basis, I can write R, theta, phi, which is just an expanded way of writing this K. Okay, I spell out the variables R, theta, and phi, N, L, M, L, and this will give me a radial part that only depends upon R, okay, multiplied by an angular part which I have denoted by Y, which depends upon the parameters theta and phi. This R is indexed by the variables N as well as L. Remember that even though the energy only depends upon N, the wave function, the radial part of the wave function does depend upon N and L. This is something we saw in the recitation when we derived the radial part of the wave function, solution to the radial part of the equation. So this wave function does depend upon N and L. This Y, this spherical harmonic function depends upon L and ML. It's indexed by L and ML, and it's a function of theta and phi. So this is what we call the wave function, R, theta, phi. Okay, and these are the eigenstates of this central potential system. Different potential energies will give you different radial wave functions, but the whole angular wave function will always remain to be equal to the spherical harmonic functions. Because what is changing in real systems is just this potential energy VR. For any central potential, this is the Schrödinger equation. Only thing that changes is this potential energy function. So all central potential systems will have the same angular parts to the wave function, which are the spherical harmonic function. They will have an S orbital, a P orbital, a D orbital, F orbital, and so on, the same shape. The only thing that is going to change is the radial part of the wave function. So this is something for you to keep in your records, and you will given a copy of this in the exam or quizzes as well.
हमारा स्पिन नहीं आया,
स्पिन नहीं आया, वो यहाँ से आया, आ भी नहीं सकता। ठीक है, इसमें बहुत सी अप्रोक्सीमेशन है। देखो, we have ignored spin, no spin. Okay, so there is no coupling between spin. There is no spin in the first place. There is no coupling between L, the orbital angular momentum, and spin. Okay, because there is no spin. So there are certain assumptions in this model. We haven't taken into account spin. For example, now this is a spherical symmetric system. The hydrogen atom, for example, with the center of tension. Suppose I have a cylindrically symmetric system. For example, a molecule in which a spiral, like a helical molecule in which an electron can go around a helix on the surface of the system. Okay. Now, for this system, I would like to come up with a set. It's a three-dimensional system, no doubt. I would like to come up with a set of three mutually commuting observables. Okay. I know the observables. One of them is the Hamiltonian. What else is conserved from this system? Is there anything else that is conserved? So in this system, the spherical symmetric system, the total orbital angular momentum is conserved and the z component of the angular momentum is conserved. Okay? These are all conserved quantities. Whenever you have a symmetry, you have some quantity that is conserved. This is a basic principle of physics of quantum mechanics. So here, Hamiltonian tells you the time evolution of the system. It tells you how the system evolves with time. It's a generator of time evolution. So with time, there is something that doesn't change. And that observable which doesn't change commutes with the Hamiltonian. So can you think of an observable that doesn't change with time for this system? Which angular momentum?
so radial angular momentum.
The radial angular momentum.
So radial constant.
Right. LZ. This system does not change if you rotate the system about the z-axis. If I define this to be the z-axis, right? Okay. Can you think of another observable that doesn't change with time? L square. No, L square will change. It's not spherical.
But since LZ commutes with L square,
That does not mean that L square also commutes with H. If you have two observables A and B that commute, and B commutes with C, that doesn't mean that A commutes with C.
that's what we established that as well.
No, but we proved that by explicitly.
No, the question L square का part था LZ, तो वो करेगा.
तो बताए कोई और ऑब्जर्वेबल, कोई मोमेंटम ऑपरेटर किसी तरह का जो कि कांस्टेंट ऑफ मोशन होगा, PR. देखो PR जो है ना, खाली PR is not an observable. PR is not Hermitian. PR square is Hermitian. PR is not an observable. Remember this. What about PZ? You translate this system about the z-axis. Nothing changes. So this is a set of mutually commuting observables called a complete set of commuting observables, CSCO. Okay, and the quantum numbers associated with these operators will define your wave functions, which are the eigenstates of the Hamiltonian, and will also be eigenstates of this operator and eigenstates of this operator. Okay, so this is a cylindrically symmetric example. Now I would like to come up with one example. an explicit calculation.
Cylindrically symmetric हम बनाएंगे ऐसे सब
क्या?
Cylindrically symmetric potential कैसे बनाएंगे?
यानी अगर आपके पास एक मॉलिक्यूल है, ठीक है, जो इस तरह हेलिक्स के अंदाज में ट्विस्ट हुआ हुआ है, the electron is constrained to move on this one-dimensional helix. So this is like having a potential that is cylindrical. It is there are different ways of doing this. Let me give you a more real example. An example that I would give you forms the basis of all kinds of spectroscopy. I would like to talk about, first I would like to talk about the rigid rotor. The rigid rotor. Suppose I have a diatomic molecule, say hydrochloric acid or hydrogen H2. Now, of course, it has two nuclei. Okay. There is a center of mass and an axis of rotation. Okay. Suppose this is R1, this is R2. And the equilibrium distance between these nuclei is R0. The moment of inertia of this molecule, the reduced mass is mu. The moment of inertia I will be equal to mu R0 squared. Now this molecule, say a hydrochloric acid molecule, nitrogen gas, any diatomic molecule, is rotating about this axis. Okay? And this axis can itself rotate in space. So it can make three-dimensional rotations. Right? It's a gas, so this axis itself can rotate. So it's a molecule that is rotating in three dimensions about its center of mass. And it's called rigid because we suppose that this distance between the nuclei doesn't change, which means there are no vibrations. Okay? We're decoupling the vibrations from the rotations. And later we'll see that they are at different energy scales, so we can decouple them. So this is the physical model of a rigid rotor. Okay. Now we would like to write the Hamiltonian for this system, for the molecule. Now we talk about the molecule. Okay. And we ignore the potential energy of this term. Potential energy is always with reference to something. So if you have an electron near a nucleus, near a proton, the potential energy is due to the electrostatic interaction. Here there is no interaction of this molecule with anything else. It's a gas. It behaves as a gaseous particle. Okay, no interaction with neighboring gas molecules, so the potential energy is zero. So we would like to write the Hamiltonian H.
So one question, for example, in hydrogen, we were taking the V as a proton with respect to electron.
V क्या?
जो potential था.
हाँ, potential.
ठीक है. इधर हम H with respect to scale क्यों नहीं गए?
देखो इन दोनों के दरमियान कोई ना एक है आयोनिक इंटरेक्शन, ठीक है। अगर ये एक आयोनिक मॉलिक्यूल है, HCl एक आयोनिक मॉलिक्यूल है, अगर हाइड्रोजन की बात करें कोवलेंट इंटरेक्शन है, ठीक है, इनके एक बॉन्ड बन गया, एक मॉलिक्यूलर ऑर्बिटल बन गया, ठीक है। अब वो जो इंटरेक्शंस जिनकी आप बात कर रहे हो between these ions, for example, this is an ionic compound, they are electrostatic. They occur at a different energy range. Okay? And we look at these energy ranges. So the rotation occurs in a different energy regime. So we can decouple the two. Okay? I'll explain this in a while. Okay? So there are different energy regimes in which the rotation occurs, in which the vibration occurs, and in which those electronic or these electrostatic interactions occur. Okay? So now we're treating this molecule just as a rotor. It's just rotating. Now, if this molecule is just rotating, can we write, is it simple to write down the Hamiltonian for this system? What's the Hamiltonian?
P square root.
Not P square, it's going to be rotational parameter. It's going to be L square over 2I. Okay?
So it's going to be R square minus 0.
Right. ठीक है, L square over 2I. अब ये आप सिस्टम लो, अच्छा I is a constant, it's just the moment of inertia of this molecule. Now label the waveform, the eigenstates of this system. How many quantum numbers are required?
Square case
Instead of L.
into L.
L. So I can have a quantum state, I label it by L. Okay? So when this operator H acts on L, I get H bar squared N plus 1. Sorry. Sorry? N क्या है दोस्तों, कोई फर्क नहीं पड़ता, कोई भी आपने वेरिएबल लेना, एक वेरिएबल लेना, ठीक है? देखो, L square when it acts on this state, it gives me H bar square L into L plus 1. This 2 items here. This is an eigenstate, L, right? But we're talking about Hamiltonian here. So all of this is simply the energy, En, which is labeled by the quantum number N. Okay, you can call it N if you like. Doesn't harm, but it's conventional to call it, label the eigenstates of the total orbital angular momentum by L. So now the Hamiltonian is given by L square over 2I. There is no radial momentum, because radial momentum would mean that this molecule, it doesn't make sense here.
Rigid.
Rigid. Okay. So L square over 2I की जो L square की eigenstates है, एक eigenvalues है, H bar square L into L plus 1. ये 2I यहाँ है, ये constant है. Since this is an eigenstate, वैसे का वैसे. चूंकि ये Hamiltonian है, इसलिए all of this should equal the energy. So now we have the energy, the rotational kinetic energy, which we're talking about here, is quantized, and it's quantized according to the number L into L plus 1. Okay, so now L can take up values from 0, 1, 2, all the way up to infinity. There is no n here, remember. It can take up all of these integer values. Okay, so if the molecule is in this state, it's called the rotational ground state. If the molecule is in this state, it's the first excited rotational state. So these states are, if n equals 0, the rotational energy is 0. Okay, the rotational energy is 0. But there are other forms of energy will never be 0, so that the 0 point energy, the uncertainty is still satisfied. There are other forms of energy for this molecule as well. So the rotational energy is nevertheless 0. Okay? Then if n equals 1, this becomes 1 into 2. Okay? Then this becomes 2 into 3, which is 6. So the spacing between these levels keeps on increasing. This is the rotational ground state, first excited state, second excited state, third excited state, and so on. Okay? Now, what is this difference equal to? This difference equals simply H bar square over 2I. In other words, you can compute the energy difference between two adjacent states, delta E. Delta E is between L and L plus 1 is given by H bar square over 2I L plus 1 L plus 2 minus L plus 1. This is H bar square 2I L plus 1. So the energy spacing keeps on increasing with L. Okay? Now, sorry. Okay? Up देखिए, if you would like to have the rotation ground state of the molecule populated, what is the temperature that you you're cooling down a molecule and you would like only the rotational ground state to be populated. What temperature would you take? This is a question of general quantum mechanics. You want to populate this state. This is your desired state. that is all your molecules are in the rotational ground state. You want to freeze the motion of the rotational motion of your molecules.
0 Kelvin, sorry.
0 Kelvin, like 0 Kelvin, GP Kelvin. So what is the order of magnitude of the temperature that would ensure that most of the molecules are here?
Sir, already OCS निकालेंगे at least 90% या कुछ जो 0 स्टेट पर है।
तो कैसे निकालें?
उस पर एनर्जी निकाल दें।
ठीक है। यानी इसके अंदर जो molecules की जो fraction है n in the ground state will be given the E minus the energy of this state. What is the energy of this state? 0. Sorry?
इसका वेव फंक्शन निकाल दें।
नहीं इसकी इसको एक और तरीके से सोचो। If my temperature kBT is much smaller than h bar square over 2I, that is, my temperature is much smaller than h bar square over 2I kB, then this will ensure that the rotational ground state will be predominantly populated. If the temperature kBT, the thermal energy is not enough to overcome this barrier, then that would imply that this rotational ground state will be populated. Okay? So, is it easier to achieve the rotational ground state for hydrogen molecule, or is it easier to achieve it for the fluorine molecule?
So why?
Which would require lower temperatures
So
to achieve the rotational?
Why h bar square over 2I? Not why not h bar square over I? जो L equals to 1 और L equals to 0 का difference है. Difference है h square. H bar square over I.
Sorry. ठीक है.
2 नहीं है. 2 नहीं है.
थोड़ा सा ये तो बिल्कुल सिंपल सी चीज़ है, इसको देख लो। h bar square मैं ये डिफरेंस अगर देखना चाह रहा हूँ तो ये है 1 h bar square over I, इस पर्टिकुलर स्टेट में ये h bar square over I, ठीक है? चलो, is it easier to make the rotation ground state for hydrogen or fluorine, which would require a higher temperature, which necessitates a lower temperature? In other words, that will be more difficult to make. Fluorine is harder because fluorine has a higher moment of inertia. The temperature requirement is more stringent for fluorine. So it's easiest to make the rotational ground state for hydrogen. And chemists would know that if hydrogen comes into the ground state, rotational ground state, because of the Pauli exclusion principle, the spin becomes different. So this is called parahydrogen. Probably if I have time, sometime I will explain what parahydrogen is. But if we can make the diatomic molecules go into the rotational ground state, one can tell that one can actually tell what the temperature is. If you know the fraction of molecules in this state, the fraction of molecules in this state, you can tell what the temperature is. Okay, now how do you tell that? You use the Boltzmann distribution. If the fraction of molecules in the state, say A, if I would like to calculate Na over Nb, the fraction of molecules in the rotational state A divided by the fraction of molecules in the rotational state B, this would simply be equal to E minus E in the state A divided by kBT, E minus EB divided by KB. Right? This is just the Boltzmann distribution of how these states are populated with respect to temperature. Now this is quantum statistical mechanics. This is how we put in temperature into quantum mechanics. So this will become E minus EA minus EB over KBT. This is E minus delta E over KBT. Now what is my delta E? Delta E is simply H bar squared N plus 1 over 2I KB. This will give us the relative fraction of the molecules in two states. Okay? Now we talked about the rigid rotor, and still we need to know an order of magnitude estimate of what this energy difference is. Okay? Because I would also like to answer Asad Alam's question. But let me talk also about this molecule, the same molecule, in which vibrations are also done. Vibrational states. Now, if you talk about the vibrational states, this molecule is behaving like an oscillator, like a harmonic oscillator. So now its potential energy Vr will depend upon the distance between. R now defines the distance between these two nuclei. Okay? So this Vr will of course have some bias term V0 which can be ignored to 0 plus half partial square V partial R square at the minimum, which is the equilibrium bond length, into R minus R naught square. Okay? Plus higher order terms which can be neglected. So it's like a potential energy function. In this region, at R close to R naught, one can approximate the vibrational manifold of this molecule by the harmonic oscillators. Okay? And we already know that for a harmonic oscillator, this molecule is now behaving like a harmonic oscillator. The energy levels will be equally spaced.
So, अब n आ जाएगा.
अब n उसको n कहते हैं. So now n represents the vibrational quantum number, and the energy, the Hamiltonian for this. What's the Hamiltonian for this system? It's the Hamiltonian for the harmonic oscillator. H bar omega number operator n plus half. Okay, it's the same. It's the harmonic oscillator now, and the vibrational levels are now denoted by n. Okay, so this gives us the energies. The energies will be h bar n plus half okay, and this energy spacing between two adjacent levels is constant, h bar omega. Now how do we get this omega? The omega is hidden here. Half a square. So this term is k is omega square, the reduced mass mu. This term is omega square mu. Okay, this is our model for the harmonic oscillator. Hence, the omega for this system will be given by 1 over mu, the second derivative of the potential energy with respect to R at the equilibrium square. Now, these are the vibrational levels of the same molecule, and these are the rotational levels of the same molecule. We need to actually know what this energy spacing is as compared to this energy spacing. If this energy spacing is smaller, each vibrational level will contain many rotational levels. If this is smaller, then each rotational level will contain many vibrational levels. So we would like to see how one is nested inside there. सही बात ये समझ आ रही है?
So और फिर जो हमारी आइगन स्टेट होगी वो इन पर डिपेंड करेगी दोनों पे.
इस वक्त जो हमारी आइगन स्टेट ऑफ दिस रोटो वाइब्रेशनल सिस्टम, इट्स अ रोटो वाइब्रेशनल सिस्टम. The eigen states can be labeled like this: N, L, where N and L are totally decoupled. Okay, you can also write this as N tensor product with L. Right, so this is the quantum state of the system. You can put this in the position representation or the momentum representation. You know how to put these number states in the position representation. Okay. Alright. Now we need to know the energy scales of this vibrational spectrum and for the rotational spectrum. इसलिए हमें ओमेगा निकालना पड़ेगा और इसलिए हमें ये आई निकालना पड़ेगा. ठीक है, तो एक रफ एस्टिमेट से करके देखते हैं. और मैं ये जरा थोड़ा सा जल्दी में करूँगा. तकरीबन 10 मिनट. I'm going to use dimensional analysis to get order of magnitude estimates for these energies. We know that in a ground state, let's call the energy E1. If we want to find, I put 1 here because suppose I have a hydrogen molecule, okay, an electron in its ground state inside this hydrogen atom. So I label the N is equal to 1, so I put E1. So E1 is just the expectation value of P square over 2m minus the plus the potential energy. The potential energy is E square over 4 pi epsilon R. So E represents E over 4 by epsilon naught. So I just use this notational convenience. Okay. So this is my E1. Now this means that this is 1 over 2m P square expectation value minus E square the expectation value of 1 over R. Now typical length scale in the atom is A. For example, this would be the Bohr radius. Okay. Now I have to find the expectation value P square. Okay. Value 0, so you get this. Okay. Now the expectation value of the momentum operator is 0 in the ground state. Okay. So this turns out to be delta P square. Now from the uncertainty principle, I know that delta P into the typical length scale A is of the order of h bar. Okay, so this becomes h bar square over a square. All of this is approximate, remember, which means that this energy E1 is h bar square over 2m a square minus e square over a. This is E1. Correct? I just put in the value of P square. This is my E1. I can use this to find A. Small a is the length that minimizes E1. Okay? So I take the derivative of E1 with respect to A. I put it equal to A. This derivative is h bar square 2m a minus 2 minus 2a minus 2a e square a minus 1 plus 1 over a square, right? Put this equal to 0. I can use this to find a square over e square equals n a cube over h bar square. This means my a equals h bar square over n e square. So this is a typical length scale. This is called the quantum length scale, defined by the Planck constant. Okay. You will find that this is almost equal to the Bohr radius. It's about an angstrom. A typical length scale. Okay. Now I put this value of A in here. I can get E1. So this E1 is minus MT4 over 2h bar squared. I just take this value of small a and put it inside E1. Now this is a quantum length scale. This defines the regime in which effects become quantum. Okay? And this defines a typical energy scale in the quantum regime. Okay? This is almost equal to the Bohr radius, and what will this be equal to in electron volts roughly? About 10 electron volts. Okay? Precisely it's 13.6 electron volts if you do it properly through wave mechanics, not through this hand waving Heisenberg uncertainty principle. Okay? So this is a typical length, and this corresponds to optical transitions. This number corresponds to optical transitions because from a hydrogen atom you get either optical radiation or ultraviolet radiation. The Lyman is ultraviolet, Balmer is visible. Passion bracket, they are infrared. So you get the UV to visible range at these energy differences. Now what we would like to find out is we would like to first of all find out what this term. Let's first find out this term. A typical length scale. Okay? The typical energy scale. We have to finish it, just 5 minutes. Now omega is 1 over mu. Now this mu is generally the mass of the nucleus we're talking about. Suppose both nuclei, it's a homonuclear nucleus, both of the nuclei have the same mass, Mn. Okay? Now partial square over partial r square. Now there is a potential energy and there is an r squared. It's the second derivative. Now the potential energy is of the order of E square over A, right? Correct? Which means the double derivative of this by dimensional analysis will be E square over A cube. Okay? Just look at the dimension. This is the double derivative with respect to this length scale. So it's partial E square over A cube. Now what we are supposing here is that the dimensions of the molecule, the size scale of the molecule is the same as the hydrogen. Okay. So we are at the dimensions of the atom. So this E square over A, which is this thing, this is E square over A cube, and you take the square root of this. Okay. Now I just plug in the values. 1 over Mn E square. Instead of A, I plug in the value that's over there. H bar square. So I have H bar is for 6. I have M square N2 V6 N2 E6. ठीक है? E6 इस स्क्वायर से आगे E8 हो गया और इसका स्क्वायर रूट लेना है। तो मैं क्या करता हूँ? अच्छा ये M कौन सा? ये M इलेक्ट्रॉन का है। ठीक है? We talking about the electron. This A is defined in terms of the mass of the electron. So what I do? I take this Me over Mn, and here I am left with a square.
So जो Mn है that is for
nucleus,
some.
for the nucleus. Okay? So मैंने क्या किया? E8 इसको मैं हाफ में लिख लेता हूँ, ठीक है? अच्छा E8 का स्क्वायर रूट लिया E4 आ गया, यहाँ जो ME स्क्वायर बचा था उसका स्क्वायर रूट लिया ME आ गया, ठीक है। ये H बार रेज़ पावर 6 का स्क्वायर रूट लिया H, this is what I get, okay. Now what is this? This is simply E1. Okay. ME4 with H square था, H2 होना चाहिए, सॉरी ये देखो ना H square divided by H is 1 4 H2 है, ठीक है, ये H2, ठीक है। अब this is E1. Now what we have, mu typically is, this is typically of the order of ME, MN. By the way, this is H bar mu, H bar mu. Sorry, H bar mu. Sorry,
ये ओमेगा ही है।
हाँ ओमेगा E1 dimension E1 भी H bar mu रहना चाहिए, लेकिन वो
H bar square ये कैंसिल हो गया है, E1
सॉरी ये H bar square है, सॉरी H bar square है, और यहाँ पे ये वाला एक बार यहाँ, ठीक है। अब वो क्या है, अब देखो ये जो एनर्जी स्पेसिंग है बिटवीन एडजेसेंट लेवल्स, एडजेसेंट वाइब्रेशन लेवल्स, इज इट स्मॉलर देन E1 और बिगर? दिस इज ऑफ द ऑर्डर ऑफ 10 इलेक्ट्रॉन वोल्ट्स. What is this energy equal to? Is it smaller? Smaller by a fact, by a certain factor. The mass of the nucleus, the hydrogen nucleus, is about 1800 times heavier than the electron. So you take the square root, this factor turns out to be roughly 1 over 40. So if you're talking about 10 electron volts for the electronic transition, for the vibrational level, this spacing is 40 times smaller. So if you're talking about the visible regime over there, in the vibrational regime, you're talking about the infrared, near infrared. Likewise, you can do a similar kind of calculation, H bar square 2I, and you put I equals to 2 mu A square, okay? Where I is the moment of inertia, which is the reduced mass into A square. You plug in these values, you'll get the spacing that is 1 over 40 times even smaller. So what do we have here? We have a big spacing between the electronic energy levels. Inside each electronic manifold there is a vibrational manifold. And inside each vibrational manifold there is a rotational manifold. So if this energy is of the order of tens of electron volts, this energy will be of the order 1 over 40 times smaller, of the order of hundreds of milli electron volts. This will be of the order of micro electron volts. Likewise, the wavelength of the radiation absorbed and emitted will change. The wavelength will increase in this direction. So if this is in the ultraviolet or the visible regime, this is in the near infrared regime, and this is in the infrared or the microwave regime. So rotational spectrum is generally involves microwaves or far infrared waves. This involves near infrared waves. So this is how the energy spacing takes place, and this is totally decoupled from this manifold, and this is totally decoupled from this manifold. I think I've done enough of three-dimensional quantum mechanics. On Monday, I'm trying to come up with a homework today so that we do enough practice with the three-dimensional wave mechanics. On Monday, I'm going to start the time-independent perturbation theory.